I think that should actually lend itself to making our notes a little bit faster today. So here we go. Exponential functions with base e are frequently used in an alternate form of exponential growth formula that represents situations involving continuous growth. And wouldn't you know it, there's that function right there that we just used on number 55. It's the same thing as the continuously compounding interest formula, just has slightly different variables. So A is the initial value, T is the time in years, K is a constant representing the rate of continuous growth, which is always given as a percentage, but we write that value as a decimal of that percentage. The continuous exponential growth equation is often used to represent population growth and is the same as the continuously compounded interest formula, of which we use both with both questions that we had from the assignment. It's great. So without knowing it, you actually helped us out in terms of speeding up our lesson a lot. So thank you. Those are the variables. That's what they represent. We've used these both already today. So let's just go ahead and jump into this first example, because I think we'll be able to move pretty quickly today. We're talking about Florida and the population of Florida. So in 2016, 2016 was 8 years ago. Geez. The population of Florida was 20.61 million people. In 2000, it was 15.98 million people. And it doesn't really tell us what we're doing, but it tells us to write an exponential growth equation. So we know that we have a beginning value and we have an end value. So we have an A and we have a Y. So we also have a time as well. What we don't have is a value of K. We don't have a population growth rate. So I'm guessing that's probably what we're solving for. So here we go. Because population, because population is growing as time passes, you're going to use the year as the independent variable, X. And the population is the dependent variable, Y. Find the value of K, Florida's relative growth rate. Then write an equation that represents the population of Florida at T years after 2000. So since T is the number of years after 2000, blank represents the initial population. What is the initial population here? What was the population in the year 2000? Yeah, 15.98. Now, just keep in mind, that represents million. So I'm just going to write mil next to that because we would need plenty of zeros. And blank represents the population 16 years after, so 20.61 million, 21 million, 16 years after 2000, or at the value of T equal to 16. So it takes 16 years for the population to increase from 15.98 to 20.61 million people. Cool. So we'll be able to write a function based off of that. And I think we're going to end up solving for K, which is in the exponent, which means we'll need to use natural logarithms in order to solve for K. So turn the page. So here's our formula. The value on the left is the current population of 20.61 million. And we have, that's going to be equal to 15.98 times e to the K times 16th power. We need to isolate. We're solving for K here, by the way. We're figuring out the growth rate. So if we divide both sides by 15.98, that is going to isolate the power, e to the 16K. And then we apply our natural logarithm, the property of equality for natural logarithms. That's going to be ln. The ln and the e are inverse operations. Therefore, they will cancel each other out, leaving us with only the exponent, which is 16K. So we've got the ln of 20.61 over 15.98 is equal to 16K, which means to get K by itself, we'll divide both sides by 16. And if I was doing this one, actually writing everything out, I would definitely put the 20.61 divided by 15.98 in parentheses because your calculator will also do that. So that's why I'm putting parentheses around those. So the value of K, the rate of growth for Florida between 2016 and 2020, they're relative. No, 20 2000 and 2016, 16 years. The relative growth rate over those 16 years is about 0.0159, or what percent would that be? 1.59, yeah. Just move the decimal over a couple of spaces. Boom, boom, right there. 1.59%. Continuous growth. Cool. And if you were to write an equation for that, now that we have the value of k, we would get y equals 15.98 times e to the 0.0159t. Just like what we looked at in the problems 41 and 55 from the previous lesson. Now, there's a note off to the side here. And I do want to mention this because it says that there are some assumptions here. We know that populations cannot grow indefinitely, right? Like populations will grow at times and sometimes populations shrink. Now, within those growth and shrink timelines, you can estimate a general rate of increase or decline. But those factors could be affected by land area, resources, diseases, and so on. However, assuming that a population will continue to grow at the same rate allows us to represent the situation with an exponential growth equation. This actually is a lot like the final question that we had on our test a couple of weeks ago, or this explanation anyway, because, let me go ahead and bring this up real quick. Your test a couple of weeks ago on exponents and exponential functions, the very last question of your test said this. A data set is modeled by an exponential function. Maybe it's a population that's growing. The coefficient of determination r squared is very close to 1, meaning it's almost perfectly exponential. Will predictions based on values far outside of the data set be reliable? Now, far outside of the data set means an x value that's either a lot further along or a lot further back. And the answer is not necessarily. Because if you have an actual data set, that's information that you are taking over a certain period of time. And if it shows a wonderfully exponential growth curve, it doesn't mean that it will always continue that way. Because things change over time, factors change over time. So the answer to that one is right here. Not necessarily. There's never a guarantee that the data that you collect will continue on that exact path forever. There will be no guarantees of that. In fact, it's probably more likely that it won't continue that way, depending on what information you're gathering. So, yeah, it seems like, if you have an r squared 1, oh man, okay, it's just going to continue on and on and on and on. But it's not just an equation. It's actual data. There's a difference between taking data and writing an equation and then using that to make predictions versus here's an equation, let's just go ahead and run that out forever. The second option, it will always do that because it's just an equation that has no context. But if you have actual information, actual data of the population, there's no guarantees that it will always continue along that path. So that's exactly what's being said here. All right. Population in Florida can be modeled by the function. Great. All right. When will the population reach 25 million people? So I feel like it might already have done that in real life. Let's find out what this says then. When will the population reach 25 million people? So we want to know, based on a starting value of 15.98 million, when is it going to reach 25 million? So we're going to substitute in 25 for y. We're trying to figure out how long it's going to take. So we're solving for t, which means, again, we're solving for an exponent here. So we will use natural logarithms to do this. First thing we're going to do is take 25 divided by 15.98, which apparently equals 1.564. So I'm just going to write 1.564 here. Let's see, 25. I'm just going to do the math just to make sure. 15.98. Yeah, they're estimating though. I don't like that. Not a fan of that. I'm going to cross that out. I don't like that. I'm actually going to cross this out as well. I'm going to write 25 over 15.98 here. And over here, I'm going to do ln, and then in parentheses, 25 over 15.98. I would much rather not estimate at the beginning of a problem. I don't know why they're suggesting that you do that. Would not recommend. So let's see. Apply the natural logarithm. That's all great. So we got 0.0159t right here. Again, we're going to use ln of 25 over 15.98 there. And on the numerator of our fraction, 25 ln of 25 over 15.98, which means that our answer will be a little bit different in terms of the decimals here. It'll be, I don't think it's going to be that much different, but it will be more accurate. So here we go. Math, fraction. We're going to have this as our numerator, ln of 25 over 15.98 over 0.0159. So ln, another fraction, 25 over 15.98, close it off, divided by 0.0159, and 28.147. So you can tell it's not that much different, but it is different because we are more accurate because we estimated at the end of the problem as opposed to near the beginning. So I'm going to cross this off. 28.147. Let's see, 147. I like that much better. Still, it's going to take about 28 years later. So what year are we looking at? 2028, yeah. It'll happen in the year 2028. It won't happen at the beginning of the year because it's going to be about 0.147 into that year. So let's see. Almost 2 months in. So near the end of February, apparently. Now I'm curious, what is the current population of Florida? Has it beat the estimate? Oh no, we're at 22.24 right now in the current year. So 22.24. Oh, that was in 2022, 22.24. So a couple years ago. So it's gone up a little bit by then, but probably not here. So, or in, let's see, the year 2028. Cool. 2028. So, yeah, I'd be curious to see if the function that is written here, if we plugged in a 22 for t, if it would equal what the actual population was in 22, which is 22.24 million. I'm just going to do that real quick. 15.98. 0.0159 times 22. Wow, that's actually not bad. So this is using the exponential function. And this is what the population actually was. Nope, that's not right. There it is, in 2022. So the estimation says it would have been 22.67 million, when in reality it was 22.24 million. It's about a 400,000 person difference. Not bad, starting in the year 2000. So like I'd say that's a pretty good model that was used. Okay, let's keep going. Questions so far? It seems kind of like just what we did with the questions that you had from your assignment. So, all right, part C, keep going here. Compare the populations of Florida and California. California has more people, by the way. California's population in 2000 was 33.9, which is nearly double, no, more than double. And its population growth can be modeled here. So it's definitely growing slower than Florida, but it has a larger population. So that's why we're going to answer this next question. There's more people in California. The growth it's growing, but not as fast as Florida. Florida is going to come up and eventually surpass population-wise. Determine when the population will surpass. So we're both starting in the year 2000. So we're comparing apples to apples in terms of the original populations. Florida is here. It will end up being greater than California, which is here. We are solving for t. So because we have two exponential functions here, both of which use base e, there's more than one exponent and there's more than one value of t that we're going for. We do have to solve for t, but we can't isolate the power in this situation because both powers have t. So this is where we're going to start immediately using the property of natural logarithms here. So we're going to apply the ln to both of these right away. All right, so we end up with the ln of 15.98 to times e to the, all that good stuff there. All right, now, what do you notice about what's happening here on the left? Look at the left side of the inequality here versus here. What's happened? How come? Product property of logarithms right here is what it says. So just a reminder, if you have a log of two arguments being multiplied together, that is the same as log m plus log n. Or in this case, natural logarithms, because natural logarithms are still logarithms. They just have base e as opposed to another base. So you could have ln of mn equals to ln m plus ln n. I'm going to use parentheses there because ln n is a weird thing. So that's exactly what's happening from here to here. This is an argument, 15.98. E to the 0.0159t is also another argument. If you multiply the arguments together, that's the same as adding the logarithms, or in this case, adding the natural logarithms, which means we do that over here too. So we're going to say ln 33.9 plus ln e 0.0092t. And the whole purpose of doing that is because if we can separate out the ln of this value here, 15.98, and this one over here, 15.9, and if you have ln e, remember that so ln e to the x is just equal to x, meaning ln and e will cancel each other out because they're inverse operations. This whole thing here is equal to just the exponent itself, which is exactly what's being shown here. And then over here as well, this whole thing here is equal to the exponent itself, which is being shown here. So we can separate those out using the product property of logarithms. We can then use the fact that ln and e are inverse operations, and we can say, yeah, those are just going to be left with the exponents, which actually brings the exponent, the value of t from the exponent just down to the same level as everything else, which is what we want because we have to solve for t. So what's happened between here and here? So this line and this line, what happened? It tells you on the right. So if we're just, now that we have this is a regular equation. We're just solving for t at this point. So we can just subtract 0.0092t from both sides, and then 0.0159 minus 0.0092 equals 0.0067t, which means we still have an ln of 33.9 on the right side here. So ln 33.9. And then to get the term with t by itself, subtract the ln of 15.98 from both sides. There it is. ln of 15.98 subtracted. And thank goodness they didn't estimate that one. They just left it as subtraction of natural logarithms, which is what they should have done. And then to solve for t, we'll divide by 0.0067 on both sides. And the answer is 112.25. So assuming that the trend continues, the population of Florida will surpass the population of California in what year? 2112, yeah, 112 years later. So 2112, in the year 2112. Cool. So we're just using the same math that we've used in solving for different exponents or whatever else we need to, given different parameters. So any questions before we look at another one? Got a little bit more to go through. Maybe we'll go through all the examples. Maybe not. I don't know if we will. Because there's another carbon-14 example in here, and we just went over a good one in the notes. But when I post this online, I will have everything filled out. Whether or not we get through all the notes with this lesson, I will definitely post all the answers in the notes online when I post it. So here we go. Science. An experiment that starts with 20 bacteria A cells. After 45 minutes, there are 710. Is this exponential growth or decay? Growth, yeah, it started with 20, another 710. So it's going up, exponential growth. Write the equation that models the number of bacteria A cells Y after T minutes. Round the value of K to the nearest 10,000. So T is minutes. What's our value of T? Just do some stuff off to the side here. What's our value of T? How long did it take? 45 minutes. So T is 45. What is our value of Y? What's the current amount of bacteria? $710. How much should we start with? 20. Cool. So for part A, we have to solve for K. We're using this. We're going to solve for K, which is an exponent. So block that off real quick. We're going to have 710 equals 20 times E to the 45K. We're finding a growth rate here. So divide by 20. What's 710 divided by 20? $710 divided by 20. 35.5. All right, equals E to the 45K. Apply the natural logarithm to both sides here. So we're going to get ln 35.5 equals 45K because ln E would cancel each other out. So we're just left with the exponent 45K. Divide both sides by 45. So K is going to equal ln 35.5 divided by 45. So the growth rate, let's see. Notice how quick these problems can actually be. They don't actually take that long. There's a lot more writing than there is math. We're looking at about what, 7.9% growth rate? Doesn't tell us what to round it. Oh, wait, it does. Nearest 1,000. So yeah, that's the nearest 1,000. So that means that K 0.079, which equals 7.9%. Cool. But it does tell us to write an equation as opposed to just solving for K. So let's go ahead and write Y equals AE to the 0.079 T. We'll write that. But if A is 20, we can always use 20 for A. So, which is what we're going to do for part B. After how many minutes, so this time we're going to solve for T, after how many minutes will there be 1,000 bacteria cells? So if we end up with 1,000, that's going to be 1,000 equals the initial amount, 20 times E to the 0.079 T. How much time is that going to take? All right, what's 1,000 divided by 20? Okay. Was it 15? Okay. Equals E to the 0.079 T. So then we're going to get ln 50 equals 0.079 T. So ln 50 equals 0.079 T. So that means that T is going to equal ln 50 divided by 0.079. So round to the nearest 10th if necessary. How long is it going to take? Yeah, about 49.5 minutes. 49.5. Cool. These are actually pretty short problems. Not bad at all. Bacteria B grows exponentially according to this model. So bacteria A is what we were dealing with parts A and B. For part C, though, we're dealing with bacteria B. It uses this growth model. Starting with 52, it's got about a 6.4% growth rate over a certain amount of minutes. After how many minutes will there be more bacteria A cells than bacteria B cells? Okay, so I'm just going to do this one off to the side here. So bacteria A is this one here, 20 e to the 0.079 t. So we're going to find out, let's see, 20 times e to the 0.079 t. When will that be more than? Just like the population question. When would Florida surpass California? How long is it going to take for A to pass B? Is greater than 52 e to the 0.064 t. Once again, because we're solving for t, and t appears in multiple powers, we're going to start by using natural logarithms. In fact, I'm just going to go ahead and do natural logarithms and the product property of natural logarithms all at the same time. What I mean by that is I'm going to write ln 20 plus ln e to the 0.079 t is greater than ln 52 plus ln e to the 0.064 t. Just to speed things up a little bit. You can skip steps once you recognize what's about to happen with these types of problems. In fact, if you wanted to, you could have started by, or going straight from here to the next step, which ln e's cancel out. So if you wanted to just start, go from this first step to the next one, which is going to say ln 20 plus 0.079 t is greater than ln 52 plus 0.064 t, that would be just fine. If you know where it's going, go for it. Then we got to get everything with the t's to one side. So we're going to take 0.079. We're going to subtract 0.064. That's 0.015. We are going to subtract ln 20 from each side as well. So I'm just going to write 0.015 t is greater than ln 52 minus ln 20, just combining a couple steps here and there. It's going to happen anyway. And then we'll finish off by dividing both sides by 0.015. So t is going to be greater than ln 52 minus ln 20 divided by 0.015. So it's going to take, let's find out how long this is going to take. It's going to take more than, how long will it take more than? ln 52, close the parentheses, subtract ln 20, close that one, divide by 0.015. It'll take just over an hour. 63.7 is our answer. So about an hour and 4 minutes, nearly. 63.7 minutes will be our answer to that one. So 63.7. Cool. Yeah. I don't know about you, but it's kind of nice knowing what formula needs to be used because it really limits what you can do with those equations and how to solve them. Keeps things pretty contained. Okay, questions here before we continue? All right. So I do want to talk about some exponential decay real quick. Yeah, the carbon dating one, we're going to skip that last example because we had a carbon dating question from the assignment already, from yesterday or from last week. So we'll finish with this example here using logarithms to solve exponential decay problems. So exponential functions with a base of e are frequently used by researchers and scientists to represent situations involving continuous decay as opposed to continuous growth. So decay, what's the only difference here in this function versus growth? What's that? The negative, yeah. So negative implies that the growth rate is negative. as opposed to positive, which means it's decreasing as opposed to increasing. So A is the initial value. K is a positive constant representing the rate of continuous decay, but it's the opposite of that, so that means it's decreasing. So here we go. The half-life of a radioactive substance is the time it takes for half of the atoms in the substance to disintegrate. The radioactive substance, thorium-230, sounds like something from Marvel, is used to determine the ages of cave formations and coral. The half-life of thorium-230 is 75,381 years. That is a long half-life, I think. I don't know. I don't know much about how long an actual half-life is. It seems like a long time to me. All right. Let's keep going. Part A. Determine the value of K in the equation of decay for thorium-230. So again, half-life just means you're going to end up with half of the original material. So over here, it says, kind of like what we did in the question from your assignment, 0.5 A goes there. A goes here, and then when you divide by A on both sides, it just ends up with 0.5 on the left. Exactly what happened in the assignment that we had. The amount of time that it takes is 75,381 years. We're looking for the value of K. And so once again, once you have your power isolated, you can take the natural logarithm, property of equality for natural logarithms. And then we're going to end up with ln of 0.5 is equal to just the exponent, which is negative 75,381K. And if we divide both sides by negative 75,381, well, here it is right here, just pellets. So right down below, we can go ahead and do this because I just want to make sure we're quick here. How many zeros is that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 9, 2. Move the decimal 2 spaces to the right, and that is 0.00092% per year. Not very much. Thus, the equation for decay is there. All right. Part B. How much of a 2-gram sample will be left after 1,500 years? Most of it would be my guess. Because if it has a half-life of 75,381, it's going to take that much time for it to go from 2 grams to 1 gram. And if we're only talking about 1,500 years, yeah, most of it is still left. Over here, though, by the way, that's the half amount here, so that's going to be 1. A equals 2. T equals 1,500. Actually, no, this is going to be Y. That's not going to be 1. That'll be Y equals. Because we have a value of T, we have everything here, so there's no natural logarithms involved at all. That's all we're doing. Just plug in for T and solve. That's it. So after 1,500 years, there's still 1.97 grams out of the original 2 grams because it's decaying very slowly. There'd be about 1.97 grams remaining. Since it has such a long half-life, it's reasonable that after 1,500 years, only a small amount would have decayed. Yeah, that makes perfect sense. Cool. All right. Last example that we're going to do. Be quick with it here. Actually, are we feeling okay about this? Yeah? All right. I'm just going to go ahead and pause here. I will write in the answers to everything else before I post it to Google Classroom later today. But I think we got the idea. So for your assignments, well, there's really not very many. So we'll do 1 through 17 odds. So 1 through 17 odds. All right. Hi, Gary. So that's all we got. And we'll be out of here in less than 2 minutes.